This is a GCSE physics presentation looking at electromagnets. In front of you there's a number of statements, and each one you've got to identify as being true or false. When you're ready, you can restart the presentation and check through your answers. So pause now and try your best to come up with the answers. In terms of each of the statements, these are all key stage 3 in terms of their content, so they should not be new to you. However, you may need to go and brush up on the presentation on magnets, or you can go and brush up on your key stage 3 materials if you have them, but you need to make sure you know this stuff before you go any further through this presentation, as if you don't know the properties of magnets, you're going to get more and more lost as we work our way through electromagnets. In this lesson, we're going to look at what's called a solenoid and how it works, and we're going to look at the structure of an electromagnet. And we're also going to spend a little time looking at an interpretation of electromagnets. Please note that only applies for those people doing GCSE physics. If you are doing one of the other courses that's not GCSE physics, you do not have to cover that last section, and we'll identify it as we go through. When talking about magnetic fields, we're talking about the area around a magnet in which it'll exert a magnetic force. In terms of current flowing through a wire, well, if we have current traveling through a wire, there is a magnetic field around that wire. And if we use plotting compasses, we can actually draw those magnetic field lines. And when you draw them, you'll find that there's actually a pattern of circles around the wire. What you've got in front of you is a very simple layout where we have a battery, a wire, and a piece of paper around which the wire runs through. And what you can do is you can use a concept called the right hand thumb rule. And remember, this is the right hand one. There's another one later we'll look at called the left hand rule, but this is the right hand thumb rule. And using the right hand thumb rule, we can identify which direction the magnetic field lines are traveling around the wire. The right hand rule is simple. All you have to do is use your thumb and line your thumb on your right hand with the direction of travel of current. So if you look at the picture on the right hand side, you can clearly see a hand there. The blue line represents the wire. If the current is flowing upwards through that wire, you can see that we are traveling around the wire in an anti-clockwise direction. So the magnetic field is going anti-clockwise around that particular wire. If we were to put the current through the wire the other way, so instead of the current going up, the current going down, you would see that as we wrap our hands around, that the magnetic field lines would be traveling in a clockwise direction. At this point, you try and work out what direction the magnetic field lines in the diagram are traveling in. So pause the presentation, try and work it out using the right hand rule, and when you're ready, restart the presentation. Well, the first thing we have to do is determine the direction of travel of current. And current, we talk about conventional current, travels from positive to negative. That means that the current is traveling upwards through the paper. If we line the thumb on our right hand and point in an upwards direction, your fingers will curve naturally in a anti-clockwise direction. So the magnetic field lines, the arrows in the magnetic field lines should be pointing anti-clockwise. The strength of the magnetic field is dependent on two things. It's dependent on the current that's actually flowing through the wire, because if we increase the current, we can increase the strength of the magnetic field. But we also have the distance from the wire, so how far the object is from the wire also has an impact in the same way that we talk about the distance from any magnet. The further you are from the magnet, the lower the strength of the magnetic field. If we take that wire and we wrap it up into a coil, as you can see on the right hand side of the screen, you'll actually increase the strength of the magnetic field. And the strength of the magnetic field increases because all the field lines around each bit of the wire line up and they combine. The field lines are much closer together as well as in the same direction. As a consequence, we end up with what we call a solenoid. And a solenoid is a piece of wire wrapped up into a coil, but it produces a strong and uniform, so it's the same no matter which bit of the coil you go to, it's the same magnetic field, and it creates a strong and uniform magnetic field. It's not impossible in an exam that they will give you a very complicated looking diagram, as you can see on the screen in front of you now, and ask you all sorts of questions about it. But the diagram, you've actually already got the knowledge to be able to interpret the diagram based on the previous bit of the presentation. You know that from the diagram that the direction of travel of current is from the right hand side, it goes up around the coil and then down on the left hand side and back into the power supply. We can use our right hand rule to identify the direction of travel of the magnetic field lines. As a consequence, if we know the direction of travel is from right to left, we know that magnetic field lines leave a north pole and enter at a south pole. So we can use that to identify the north and south pole. So if we took all the magnetic field lines away, we would be able to identify north and south pole just by identifying the direction of the current as it goes around the wire. When we talk about magnetic field lines around a solenoid, we simply use the same type of pattern as you'd find with a bar magnet. Again, if you haven't done that before, go back and look through the other presentations on magnetism, and you can see the arrangement of the magnetic field lines around a bar magnet, and it's exactly the same pattern with a solenoid. Remember, solenoids only are magnetic when they have electric current flowing through them. If we switch the current off, there is no magnetic field there. They are not permanent magnets, they are induced magnets. What we can also do is we can also increase the strength of the solenoid, and we increase the strength of the solenoid by taking a piece of iron and putting it on the inside of the coils. When we do that, we end up with a much stronger magnetic field. And a solenoid often with an iron bar inside the middle of it is the basis of what's called an electromagnet. Now the next bit, this only applies for those students studying the GCSE physics course. So if you are studying GCSE physics, then you are going to be asked about uses of electromagnets. And they don't want you to memorize a list. What they want you to be able to do is to look at pictures of electromagnets and work out what's going to happen. In terms of electromagnets, what we often end up with is a circuit with the electromagnet in it, and then a second circuit that the electromagnet can switch on or switch off. When we have the electromagnet, if we close switch A, the electromagnet magnetizes. As a consequence, if B is a piece of nickel, cobalt, iron, or steel, because steel has iron in it, hence it's magnetic, the magnet will close switch B and would then complete the second circuit. There are some examples of where we can use the idea that magnets can repel each other by replacing B with, instead of a piece of metal, we put a magnet in there. And if we arrange that magnet so that the poles from the electromagnet and the magnet at B have the same pole facing each other, when the electromagnet switches on, it will actually repel B. Vice versa, we can also have two magnets, and when we turn the electromagnet on, it would attract B. And it's very much dependent on the question that they give you. There's some simple examples of electromagnets. For example, anywhere where there's recycling and they want to remove metal from particular groups of material, that's a good way of doing it. Picking metal up and moving metal. So if you think of the large cranes that move the big giant storage containers at the docks, is another good example. And of course, the classic example is a large crane at a car crushing plant or car recycling plant that can pick up cars and move them. But they always work in the same concept that the electromagnet can be turned on and off. And because it can be turned on and off, it can be used to control another circuit. So just to finish off, What I'd like you to do is to simply draw a little picture of a brain. It can be as artistic as you like, but don't spend more than a minute on it, and simply scribble inside the brain as many keywords, concepts, and different things that we've talked about during this presentation into it. Then go and have a look back through the presentation or back through your notes, and then around the outside of the brain write all the things that you didn't remember. And then the idea is that over time you try and get all the things from the outside into the brain because you can now remember them.